And thank you for all the organizers for inviting me to speak in this conference. And I'm very happy to be here. And today I will talk about an work joint with Ludmil Katsarkov and Leonardo Cavenaghi. And the title of the paper is the same of the title of this talk available on the archive. And I'll start with giving this title of the new look of the Milnor spheres is becoming from the intuition of Ludmil about how to the differentiable structure will be connected with some kind of algebraic geometry. Okay, and this is the last start. This is the last slide. It's the talk. I just mentioned this how to start with this, and first I bring some motivation of how this story starts, and the T-duality, and the T-duality is a strong Yao-Zaslow approach to mirror symmetry, and for SYZ mirror symmetry is a duality between torus bundle. We start with the pair of labials, and with like special Lagrangian fibration, and we say the pair x hat is a dual or mirror pair if the fibers are dual torus. And a consequence, you have a correspondence between the Lagrangian section of the fiber mu, the fibration mu, and holomorphic line bundles on x hat. And this duality we can interchange symplectic and complex information. This is the just hopefully speak. And in the 2004, the three physicists have another different approach to T-duality, Bognet, Hamabus, and Matai. And for this B8M T-duality, this is a T-duality now for principal torus bundle equipped with the H flux. Here, this principal torus bundle is important because this to mention for a non-principal torus bundle, this is a very recent. This is 2022 or 2023. This is the take some time to. And Bognet, Hamabus, and Matai, at the time they defining this approach to T-duality and proof at the time some topological properties of the T-dual pairs. And the idea behind this T-duality is an interchange. The charge, this is a physical language, is a charge and H flux. You need to interchange charge and flux. When the charge is the curvature 2 form, and the flux you close it 3 form. And we start with the two principal torus bundle over their same base, and we constructed this total space E. I don't know. Maybe you can look at my cursor, and E times E check over N. This is just the bundle over the same base N, but the fiber is the product of the total. Okay, and we consider the follow diagram. Okay, here's the projection of the component E and the component E check, and we consider three form invariant on the torus action, and this is the definition of Bognet, Hamabus, and Matai, and we say these two pairs are T-dual if this form is closed. Oh, sorry, is an exact form. For some torus invariant form F. And we need to ask if this is no degenerate on the fibers. Okay. And with this definition in hand, these three authors prove a lot of the key theory and the homotopy theory for these T-dual pairs. Okay. And after, we have a little bit more geometrical approach to this. This is was done by using the generalized complex structure. This was introduced by Hitchin and developed by his student Michael Galtieri. And a generalized complex structure is on an even dimensional manifold is a complex structure on the double tangent band, Tm plus T star m. And a generalized complex structure, it encompasses a lot of the structure, like a symplectic, complex, Poisson structure as particular case. And this is for us, this is a remarkable Gil Cavalcanti and Marco Galtieri. They provide a compatibility of the generalized complex structure and T-duality. Because here, all this generalized complex geometry happens in this space, and this fits very well in the diagram of the T-duality. And they show a lot of the property. I mean, if you have some T-dual pairs, and we can generalize complex structure in the both, we can interchange complex and symplectic structure, or we can fit this T-duality in sense of Bognet, Hannibals, and Matai in the sense of the generalized complex structure, and you can produce some kind of mirror symmetry. If we start with complex structure, we can look this like as a generalized complex structure, use duality, and in some cases, it will arrive in some symplectic structure. That's right, I mean. Possible twisted by some flux. Okay, and now we have another type of duality. It's called spherical T-duality. We can think this about like a no commutative T-duality, because the fiber now will be not a toric T2 or Tn, but the S3, the group SU2. And now, again, the definition comes from the three physicists, Bognet, Eveslin, and Matai. And we start with a pair, is a ST bundle, and an element of the seventh homology of the space P. And this T-dual will be another pair, another bundle, and another form, H hat, is a S3 bundle, in such a way that the second chair class of P hat coincides with the push forward of the 7 form H. And the other side, the 7 form H hat coincides with the push forward of this the second chair class of the space P. And they fit in this diagram. Okay? This is similar to the previous stuff. Okay, but now the difference, the main difference here is that the fiber is no ability. And just to mention, we have about the question about the existence and the uniqueness. If you start with the ST bundle P and the second chair class C2 in H4, and we pick some 7 form here in H7 to be the H flux. And I suppose that there exists an ST bundle such that the second chair class is prescribed by the push forward of H. Then they show that it exists another 7 cohomology class H hat, such that solve this equation. And we have this constraint the total and the correspondence space. And this construction is unique up to some additional form 3 cohomology class. Okay, but we are interested more when the base is a 4-dimensional. Okay, because if you have the base of 4-dimensional, it's a fiber 3-dimensional, the total space is 7-dimensional. Okay, but in this case, we have some exactly unity in some street way. Okay, and during sometimes people ask, oh, okay, we have this spherical duality, but what will be the analogous of the Cavalcanti-Gualtieri work? Or, I mean, what is the kind of the more geometrical meaning of this S3 spherical bundle? Okay, or spherical duality. Okay? And this is a part of our work, is put these Milnor spheres in this setup, and then look what happens. Okay? And this is just some to mention some basic notation. And now I will recall a very classical subject, but it's a very beautiful subject. It's called this Milnor manifold. Okay, and a spherical bundle. We start with the spherical bundle. Is a bundle over some base B, and we call this linear if the group structure is the orthogonal group, acting in the usual way on the sphere, or in some equivalent way, the set of transition function take values in the orthogonal group. And we have some bijection between the set of the SK less one bundle over SL and the homotopy group S of SLK of degree n less one. And if you take the special case for K is equal to L is equal to N is equal to 4, we obtain the P3 of SL4. This is P3 of S3 equals S3. And this corresponds to Z plus Z. What this means? For each pair of the integers, we can construct on a representative of this Milnor bundle. Okay? If I choose, S3 bundle over S4. Okay? For each pair of the integers. And the linear S3 bundle over S4, we call Milnor bundle. Okay. Look, this I don't claim this is a principal bundle. This is just S3 bundles over S4. This is important. And just recall the Milnor construction. This is again very classical. We start with the let's start with construction of this Milnor space. Okay, we start with a pair of integers, and the pair will represent a class in P pi 3 of SL4. And then we define maps from S3 to SL4, and this is I will describe precisely the isomorphism between a pair that represents a class in the P pi 3 of SL4 and a Milnor bundle. Okay, and here I will see S3 as quaternion of length 1, unit quaternion. Okay, let's start with Tm. I need to pick an element in S3 called X. This is a linear map from R4 to R4. This is an element here, and then apply some element V in R4, like look like this is a quaternion, and then just make this conjugation with these names. This will represent an element of the P3 of SO4. And we define in a diffeomorphism F underline TMN X comma G defined by this. This again, this action is just the multiplication of okay? And this is an element of S3 cos S3. Okay, very explicit. And now we take D4 times S3, another copy of D4 times S3, and then the boundary is exactly S3 cos S3. And we glue these two pieces by this diffeomorphism, F. Okay, we start with D4 times S3, D4 times S3, the boundary of the common bound, S3 equals S3, and then gluing. Okay. And then we define this manifold M, index M, comma N. This is the gluing space. Okay. And then this gives rise to a Milnor bond. Okay. This is a 7-dimensional space. And then some of the most famous theorem, the Milnor, is a M is a homomorphic to S7 if and only if M plus N is plus or minus 1. But it's a homeomorphic, but it's not diffeomorphic when M is equal to 2. Okay, and then this we can produce some the first example of the whole exotic sphere, Milnor 7-dimensional exotic sphere. And then we have some complete classification of this as provided after by using Kuiper. Okay. And if you denote the M plus N by K, if K is equal to 1, we have this family of manifold. And then all these manifold of this family are homomorphic to S7. Homomorphic to S7. But we have the Milnor lambda invariant. This obstructs this diffeomorphism. And then this is given by this number. Depends on the element of the family in the minus K plus 2M squared less 1 mod 7. And if you take just if you have this different of this is not 0, the manifold is not diffeomorphic to 7-dimensional sphere. But if you stick to K is equal to 1, this is all the family as homomorphic to S7. But if this lambda invariant is in this case, the lambda invariant is 4n times n less 1 mod 7. If this number is not 0, this cannot be diffeomorphic to S7. Okay. And our first remark here is we can put now these two pictures in the same. Okay, we can interpret the Milnor space as T-dual space. This is our first observation. And this, if you start with the Milnor bundle or some H flux, here we pick some integer in the 7 cohomology, the integer J, but via some exact sequence. This is just an integer, and we have this following T-dual spherical T-dual diagram. In other words, we can pass from one Milnor space to another via this duality. Okay, in some cases, but okay, look, this is a twisted by some integer here, but this we have this picture is very symmetric, right? You have some MKN in the here appears another in the interchange this M with the cohomology class. We have a lot of symmetry here in this number. This suggests a lot of you have some feeling here. There's another. We need to explore more. Let's see. Okay, but the first remark is this: we can put this Milnor construction in the spherical T-duality in the same picture. And we have, if K is equal to 1, is the same. In particular, we can construct some duality between space. One is more diffeomorphic to a 7, and another is not. Okay. And okay, but now using this symmetry, we need to explore a little bit more because look, we start to what would be this similar geometric interpretation for this Cavalcanti-Gualtieri, because we have T-duality classical, and then Cavalcanti-Gualtieri provides some geometric interpretation. Okay, and now would you like to do some similar work here, but in order to do this, you need to put some more ingredients. Let's start to look at the symmetries in the exotic spheres. And then we go back to the work, the very beautiful work of Grama and Meyer, to construct exotic sphere using some group action. Okay, just to mention very quickly here, and the study of the symmetries go back to Grama Meyer, and we start with this Lie group SP2 with the description. When we are looking here for 2x2 matrix with the quaternion entries, and we have this the projection here is a very well known, and to SP2 to S7, this is just projection in the first column, and but the first row define S3 principal action on S3 bundle. Okay, and if you collect the orbit space, you arrive in the S7, the usual S7. Okay, but Grama also consider a different action, okay, given by this. And when you take the quotient of this new action, you arrive in a exotic sphere. You arrive in another space. It's a 7-dimensional space. And now we call this the Grama-Meyer exotic sphere. What is the philosophy here? Just waving hands. You have a space. Okay, you need to decompose the space by orbits action. Okay, and what Grama-Meyer did was you unfold this, decompose this again, and glue it. You need two actions. Okay, and then you need two actions. More technically, these two actions need to commute and put this in another hypothesis. But when you have this, you can produce. You can reproduce this phenomenon in a different space. You need to decompose the space by orbits and glue it again by another different action. And then this by now is a well understood. Okay, these ideas was put in a general setup, but the work of the Carlos Duran was a student of Roma, and Rigas worked in the Campinas. And his students, Lohan Esperança and Leonardo Cavenaghi. And now we know this as star diagram construction. And just to mention, let's start a G manifold, and U a collection of G invariant set of the cover of M by G invariant set. And we can reduce to put this invariant. Okay, and we let the definition: a collection of these maps is a star collection if this satisfies this cocycle condition and this adjoint condition. And we have this very nice theorem. And if we start with the principal bundle associated to the star collection, then P admit a new action such that this is a free commute with the previous action, and the quotient is a G manifold, is a G equivalent diffeomorphic to this. This is the part as I told you need to decompose and then glue it again. But when you glue it again, globally, you have the same object, but locally is the same, but globally made different. That's exactly what happened with the Grama-Meyer sphere. This is like a conceptualization of this review construction. Okay, and we just put this in this notation. Okay, you have this some bullet action. This original action, and you need to guarantee that is it another action that commutes with the previous. and the quotient, but this new action will be this new manifold M prime. Locally look the same, but globally may not, with some structures not. But just to mention, when you put like for instance, Laurent construction new exotic manifolds in S8, in the 8-dimensional spheres, using this technology, I guess Leonardo S11, maybe. And there's another of exotic spheres in high dimensional built by this, from this perspective. But look, now we can start to do some, looking for some geometric invariant structure here. Even Grama-Meyer, the projection that I saw, this is a Riemannian submersion, when you can start to compute curvature, etc., etc. Okay, let's back again to this Milnor manifold. And just recall, we have some these two D4 times S3, D4 times S3, gluing by some different homomorphisms. Okay, now we denote this Pn by this. This time, this represents the Milnor space, and the Pn is a S3 principal bundle over S4. Okay, and then now in this setup, we can write precisely what is this two action that commute and provide this star diagram. Okay, in other words, the total space of any Milnor bundle can realize as a star diagram. This is our second remark. And here we can put this index here to provide this Milnor spheres. Okay. And the next remark here. And now, look, we have three ingredients now. We have the spherical T-duality, we have the star diagram, we have Milnor manifold. But all of three are connected. This is the first step to give this some geometric interpretation to this. If we start with a spherical T-dual pair over S4, then there exists S3, S3 manifold. This is just a manifold with two actions that commute. And you have like a big quotient and a manifold Q fitting this diagram. And vice versa. If you start with the star diagram, there exists H and H hat, such that these two guys are spherical T-dual pairs. All the three are connected. All the three concepts are connected here. And let's put some examples. If we start with this Milnor bundle, and as we saw, this is a spherical T-dual to this. And the manifold M11 is a diffeomorphic to the unitary tangent space of S4. And we can put this in the spherical T-dual. This manifold was very well stood from the point of view of the Riemannian geometry. And this is fitting this diagram. And also the Grama-Meyer sphere, exotic sphere, are T-dual to the S7, the classical S7. Okay, just to make some computation here. And we are also interested in this manifold, the 8-dimensional Hopf homotopy manifold. This is, recall the classical Hopf manifold is a odd-dimensional sphere times S1. This is a complex, non-simplex, etc. And if you fix n is one less m, we have this manifold is homeomorphic to the standard sphere, but it's not diffeomorphic. And would you like to construct a complex structure on this space, and you'd like to understand the difference. Look, this kind of question was investigated in the past by Briscoe and Van den Wem. Okay, and we call this manifold by 8-dimensional homotopy manifold, and we denote this just to shortly. This is the star diagram, and one more remark here is this: if you start with some star diagram, and if M admits a J-invariant complex structure, and only if M prime also admits. In this case, we can start to, for instance, this classical Hopf, and spread this complex structure to dual pairs. Okay, and this is in general to approach this is not trivial, but this is the advantage to work with this G-invariant setup. Because this works with G-invariant complex structure, but you can put other different structure here, and you can dualize in these in the plus one to the another. Okay, but if you put your hand into some exotic spheres to prove there is some complex structure, it's not so good. It is not so. Okay, now the second part of the talk. I'd like to discuss this generalized log transform and how it's connected with this first part. Okay. Just to recall the definition of the 4-dimensional log transform. For me here is just in a surgery. We are classical. We start with elliptic fibration. And we say the 4-dimensional X prime is obtained for X by a logarithmic transformation on the regular fiber. If we cut a turbulent neighborhood of the fiber and glue this to 2 times D2 via orientation reversing diffeomorphism. Okay, like we have some elliptic fibration, taking a fiber as a total, remove and glue another part. Okay, and the degree of this map is called the multiplicity of the log transform. And we denote by xn the manifold obtained by the if iterate the process k times. Okay, and from an original elliptic fibration over S2. And Hopf introduced the concept of nuclei of elliptic fibration. It showed that is all log transform of some space can be realized inside this nuclei of this elliptic fibration pi. This is a kind of part, okay, is called as a relevant part of the log transform. All the operation can be done inside this space, inside this part, okay? And the homotopy type of this nuclei is mesh product of 2 spheres, and the boundary of this nuclei is a Bricorn homology 3 sphere, given by this link. Okay, the 2, 3, 6 n less 1. If n is equal to 1, is 5, like we also told you a couple of minutes ago. Okay, this is the link. Okay, and but this all this concept, this definition is for 4 dimension. Okay, you would like to extend this for high dimension. Okay. And just to result by Kampf, any diffeomorphism type between the nuclei of the 2 elliptic fibration extended to the whole space. This is in fact, this is the relevant part. If you understand the diffeomorphism type of the nuclei, you can extend this for the whole space. Okay. Now, just an example, if we start with the usual Hopf manifold, S3 times S1 over S2, and then you can make this disk decomposition of this space, and the boundary is the S1 times S1 times S1, and then you have this this map, and the log transform. Okay, if it, this projection is just the Hopf map in the first coordinate. Okay, the fiber is a S1 times S1, the tons, and this is represented the Hopf map. This second part here represented the Hopf map, and this is this decomposition of this vibration. And well, how can produce some other log transforms? Is just picking some orientation preserving diffeomorphism from this tritorius to tritorius. Okay, this is like the search. Okay, and if you get if you pick one diffeom preserving here, you can conjugate by this producing another diffeomorphism and glue it again. Okay, and our suggest here a definition for a high-dimensional log transform, but this time in the high-dimensional Hopf manifold is a odd-dimensional sphere times S1, and we start again with the disk decomposition of this space. It's a disk decomposition of the Hopf manifold, and we pick another diffeomorph from this space, Sk times Sn times S1. And we say this will provide this logarithm transform. If we apply this conjugation and gluing this space, this is a kind of also kind of straight angles of this space. Okay. This is exactly the same philosophy from this previous case. And we are interested in this special case by this homotopy Hopf manifold. And in this case, again, this definition of the Milnor manifold. And for the Hopf manifold, we have explicitly this disk decomposition of the Hopf manifold, and we can choose some diffeom from S3 times S3 times S1 itself, and we can provide exactly very precise way the log transform in this H-dimensional Hopf manifold. And if you consider sigma H as the smooth manifold that are homomorphic, homotopically equivalent to S7 times S1, mod out by the diffeom. And we have this another remark. Sigma H is a Abelian group generated infinitely generate, and the log transform as an operation in this group. Okay. And now we can put all information together in the one big diagram. All of this information are connected. We have here in other words, there's operation of spherical T-duality and the generalized log transform are connected. Okay. At the beginning, what you're doing is not else like log transform. This operation in the four-dimensional elliptic vibration to produce it to shift it to another for one exotic sphere to another is nothing else like this generalized log transform. Okay, this is a kind of resurgent operation. All this idea in the same it's just in the same object like different interpretation. Okay, and but for our definition, we'd like to provide some analogous to the nuclei in the 4-dimension. Because remember, the nuclei is a relevant part of when the surgery happens. Okay, and here, just to recall, in the case of the 4-dimension, we start with this space W7 C scale as 1,3 is this it picks five complex numbers, okay, and this is the polynomial, and this is a very famous theorem from Whisper. For each k, for 1 to 28, we obtain every smooth manifold that every smooth 7-dimensional homotopy sphere. Okay? And if you denote by the L, this lower common multiplier from these numbers, defining this Wi by this, and we consider a C star action on this set here. By this action with the weights W0, W1, W2, W3, W4. And this is a homogeneous, you can consider this homogeneous, homogeneity for this. And F is a weighted homogeneous polynomial of the degree L. And each sphere S9, this is the boundary of the ball here, intersects the fiber over 0 transversally, and gives rise to weighted link of degree L of the singularity of the F. And denote by this W7, but the image of the 0, image of the 0, the fiber of the 0, intersect S9, and this is a homotopy sphere 7-dimension homotopy sphere. Okay, and therefore, if you pick K different to K prime, these are not diffeomorphic. Okay, this is the construction of Whisper. And in particular, this C star action above in the fiber over the 0 restricted to the S1 action on the same space, this W7 C scale as 1,3. And the quotient space is a 6-dimensional space V. And this is the structure of an orbifold. This was first remarked by Boyer, Galicki, and Kohler. Okay. Now we are going to restrict a little bit more, break a little bit more symmetry, reduce the symmetry now. Okay. And again, the next remark here is this: for every k runs from 1 to 28, this quotient orbifold is a Fan orbifold. Okay? And the natural question here is how these invariants of the homotopy 7 spheres interfere in the algebraic geometry of V. Okay, there's a lot of questions here. Is open. Is important. Don't know. But this will be the analogous of the R nuclei. This is the relevant part. Okay, because this will detect the exoticity. Because this is the last question give rise investigation of the new birational invariants. Okay, in particular, we have this following theorem. If K is different for K prime, then this space is not birational to this space as orbifolds. For this is open for varieties as varieties, but as orbifold is we can prove that. Look, if you start with those, in this case, this suggests if you start with two objects are not birational, you cannot because these are part of this. This is like our nuclei. if you start with no birational, the whole space are not diffeomorphic. Okay, this is the proposal. Okay? And the main ingredient to proving this theorem is develop a kind of the blow-up formula for chain one homology. Okay, this is a very, very interesting work in progress with Leonardo Cavenaghi, Ludmil Katsarkov, and Maxime Konsevity. And the philosophy here is analysis this chain one homology is like the study cohomology of fixed point, the set of fixed points of the action. Okay, and they compute the regular cohomology. But it's not the usual cohomology because the copy property is different. The copy property comes from another piece. Okay, and this is like related to this new theory provided by Katsarkov, Konsevity, Pant, and Viu. This is called theorem of atoms. In atoms, you can think like a split of the homology. How to split the homology. This is related with this, how the chain one homology split. Okay, also. And by now, this if you would like to remove this as orbifold here, you need to pass to this, find the new invariants, new birational invariants using this new theorem of atoms. Okay, and that's it.